presentation is called The Economics of Inference. It's a very good title if you ever want to write a book. It has a catchy name, The Economics of Inference. The stage is yours, Claudiu. Thank you so much.
Fabian. Good morning, everyone. I want to start off by thanking you all for being here. My name is Claudiu, and I am the head of machine learning at Veridion. Allow me to start off with a short introduction so you can better understand where I'm coming from with this presentation. Shouldn't this work? The black one. This one?
If you need me, I can act as your clicker. I've done it before.
Yeah, it's quite laggy.
It's good.
Okay. We at Veridion analyze billions of web pages every month using a vast repertoire of pretty big machine learning models. And we do all this in order to get at the essence of one question. What does every company on the internet do? In order to understand what a company does through many possible lenses, such as their location, industry, contact information, insurance profile, ESG risks, and many more, we naturally need to intensely process vast amounts of information. And doing all this while also being a startup really meant we had to take a long and serious look at the economics of such a process and find ways of making it both feasible and sustainable. I remember at the beginning of the company when we really needed to change the way we deploy our machine learning models because it was in no way scalable. No, it wasn't scalable with our projected growth, both in the volume of data we wanted to process and in the simple scope of the number of machine learning models and features we wanted to cover. So we had to make an important decision at that point, and we got an estimate for a cloud deployment solution on AWS. And the estimate was simply crippling. Simply for using our existing models, on the scale of the internet, which at that time weren't that many nor that big, the estimate was $300,000 a month back then. Yeah, you can imagine that we, being a startup, we simply had to take other routes. So we started looking at a custom solution for doing this. And after deeply analyzing what our data needs are, the volume of our data, what our model needs are, and most importantly, our data flow, the cycle of refreshness, we managed to come at a much lower number after long optimizations, albeit with a lot of work, at only, this thing is really buggy. We arrived at $20,000 a month for the same thing at the scale of the internet. That is a 15 times cost reduction, and this is what allowed us to go forward and increase both in scope and the volume of data we process. If we didn't manage this, it would have meant we would have had to take more investment earlier on, or there would have been a need for a sacrifice either in coverage, freshness, or quality, all of which we simply couldn't accept. Okay, that was where we started. Now, how it's going in this time, we have more than 30 actively deployed machine learning models that are deployed across more than 100 bare metal servers that we maintain ourselves. The amount of data we process is more than 270 billion sentences a month that go through all of our machine learning models, and we do this with a refresh cycle of less than a month. Now, this is what we'll be dwelling into today, the process of doing inference at an immense scale using a big number of large machine learning models, and how you can find ways of making this both economically feasible and sustainable. I structured this presentation by first going into the basics, the building blocks that will be used later on to arrive at some conclusions and at some concrete numbers. I have also set aside some time at the end for questions. That being said, I'd still like to encourage you all to ask questions and don't hold them until the end, especially if they're curiosities, because I want this to be more of a conversation rather than a lecture. Okay, I want to start off by foreshadowing how all of this, the process of efficient inference, all boils down to an often underestimated aspect of the machine learning world, which is model deployment. When taken at face value, this aspect, which might seem very technical at first, has deep and significant economical implications because it can oftentimes decide the feasibility of a project. Some may say we are living in an AI gold rush. This is a period which is marked by massive investments in computer infrastructure. Whether this AI gold rush is real or not, a quick glance at the metaphorical pickaxe supplier NVIDIA's stock or earnings report can tell us that the investment definitely is real. So, what is all of this infrastructure used for? For starters, you need to create these models. So the training and development stage of these AI systems surely does play a role. And for the larger ones, these systems are measured in tens or even hundreds of millions of dollars, training times in months, and infrastructures of thousands of GPUs. However, the training and development of these colossal models is barely half of the story. These models need to be deployed to become useful. And for any useful models, and that is especially true for these larger ones, most of the time in their lifetime will be spent, most of the time and money during their lifetime will be spent not in the training and the development phase, but in the inference phase at the deployment, when they are actually being useful and creating some real value in the real world. I came across an interesting statistic recently. For every $1 spent on renting a GPU around cloud providers, 50 cents of that goes towards running the GPUs, so simply electricity costs and cooling it. It's safe to say that this cost is substantial, so efficient deployment is a requirement for the payback of these significant AI systems. Let's continue by gaining some perspective and better understand what model deployment is. Creating a machine learning model is a bit like constructing a ship. You can spend many months perfecting the design, sourcing the best materials, and assembling it with the utmost precision. However, until this ship leaves the dry dock and faces the open sea, it is untested and unproven. Model deployment, it is when our meticulously crafted machine learning models face their metaphorical open sea, the real world. It is when theoretical data meets real-time applications, and when controlled testing environments give way to unpredictable life scenarios. But this transition has proved quite difficult. Let's see why that might be. First, real-world data simply is more challenging. It is messier, it's larger, and it is constantly changing. A model that performed well in a controlled setting might struggle when faced with this new reality. Secondly, we can't forget cost. Deploying and running a machine learning model is a really resource-intensive job. And cost can quickly spiral out of control, and this will lead to escalated costs that will make the project unfeasible at any relevant scale. Thirdly, there is a sure need for scalability and availability. Your models will need to handle increasingly larger volumes of data once they are deployed to production, and they will be expected to perform consistently, to be ready to answer an inference request whenever that might be given. And simply throwing more money at the problem might not work so well in this case. This is especially true in the current context because of the scarcity of acquiring new accelerators and the unpredictability of simply getting more compute when it's needed. Lastly, I bundled everything else together in a simple subpoint that deployment simply is complex. You need to worry about things like governance, versioning, working on GPUs simply is a different paradigm, and thinking requires a good technical expertise to get right. All of these details add up and can make a really big difference at the end. Okay, before getting into the economics and diving into how to make an efficient, large-scale process for deployment, we need to understand what our goal is. To answer the question, what should my machine learning or AI system do? Does it need to respond to the user queries in the blink of an eye? Or maybe it needs to churn from a mountain of data as quickly as possible. Maybe it needs to run on edge devices. For example, using some sophisticated quantization and offloading techniques, some people have been able to run foundational large language models, such as Meta's Llama model, on devices such as the Raspberry Pi. Sure, the performance did take a sizable hit, but you can't argue about how dramatically the bar got lowered for entry on using these large foundational models. Sometimes the only thing you need is to simply run the model at the lowest cost possible. Based on the needs of the system, different strategies need to be considered, and different KPIs need to be optimized for. Performance is all about how efficiently your model can churn through data. Operational metrics are all about how well your model can scale and handle increasing amounts of data and how readily it is available for use. And finally, cost, I think, needs no formal introduction. The first important performance metric I want to talk about is throughput, which is the measure of how many units of information your AI system can process in a given amount of time. Optimizing for high throughput allows your model to handle the largest volumes of data in a given span of time. However, this often comes at the cost of the time spent for a single request, which brings us to latency. Latency is the time the machine learning model takes to respond to a single query. Lower latency makes your model feel snappier and more responsive. However, this usually comes at the cost of efficiency or throughput. The most important operational metric is scalability, which simply is the ability of your model to maintain its performance as the volume of data increases. A scalable model can handle more data without a performance degradation. However, scaling usually meant scaling or compute, at least naturally. However, in this case, this becomes a bit more hard, and that is because of availability. Availability denotes the operational readiness of your model, how accessible it is. High availability ensures your model is ready to make predictions whenever it's needed. However, simply throwing more money and buying more compute, as I said, it's a bit hard in this context. GPUs are really scarce. You might need them right now, you might have the money, there simply aren't enough going around. So, in order to achieve any relevant scale, you will need robust infrastructure planning and resource management. Cost is our simple metric that will always be in a trade-off with the other KPIs and can never be ignored. All of the other KPIs will be in a constant compromise with its cost. Now, in order to understand the economics of the whole process, we need to see what our deployment options are. Which hardware is available for us for running our machine learning models at scale? By far, the most popular options are CPUs and GPUs. Let's see how they interact with performance and the operational metrics we detailed earlier, and uncover both their strengths and their weaknesses. CPUs are the most widespread compute units we have. They are virtually everywhere, and they are designed to be highly versatile, capable of handling a wide range of tasks. They are excellent at performing complex operations and are designed to handle small sets of tasks very quickly. GPUs, on the other hand, were originally designed to accelerate graphic rendering for gaming, which simply implied performing many simple calculations simultaneously. However, their ability to perform multiple tasks at once proved to be very useful in many more areas where this can be reduced to a lot of data and simple calculations, such as machine learning. Unlike CPUs, which are designed to handle a few complex tasks, GPUs are designed for parallel processing, making them excellent at performing many simple tasks simultaneously. They have a large number of cores, allowing them to have thousands of threads running at the same time. And this makes GPUs well suited for tasks that involve large amounts of data. However, there is a lot of back and forth about which is better, when one option is better than the other, and especially understand why you should choose one option on top of the other. You hear things like GPUs simply are better at matrix multiplication, or CPUs simply have lower latency, and so on. In principle, it's true that CPUs are optimized for low latency and their higher clock speeds, while GPUs are optimized for high bandwidth with parallel processing, but at a lower clock speed. But only saying this barely paints an accurate picture. So going forward, let's better understand things with an analogy. Let's say you have an important package you need to send overseas. What might your options be? Well, first, you can try to send it in a plane. That for sure will assure you that your package will arrive there really fast. The CPU is like this. It's fast due to its high clock speed. And loading a package in a private plane is pretty quick. This is analogous with the CPU's low latency. However, you can only fit so much in a plane before it gets full. And once you start needing to make multiple trips for your journey, or your package simply won't fit, the low bandwidth and the bad parallelizations of CPUs really start kicking in, and it quickly gets very slow. So, what can you do when you have a lot of packages and you can't afford doing a lot of trips with a plane, or your packages are simply that big? You can try throwing them all on a cargo ship. That will assure you that no matter how big your package is or how many you have to send, they will arrive there at the same time, albeit a bit slower. GPUs are like this in this aspect. They have really high bandwidth and are designed for parallel execution. However, their lower clock speeds makes them slower. And they have a higher initial latency. You can think of this like all the logistics involved in going to a high-level dock and loading a cargo ship, and imagine doing this for a simple small package. That will take a really long time and will be really expensive. GPUs are for the economics of scale in this case. Now that we went through all the basics, let's dive into the economics of all these options through the lenses of the performance metrics we detailed earlier. Starting with latency, CPUs are optimized for low latency and for high clock speeds, and they are very useful for cases when you only care about getting the prediction result as fast as possible. CPUs are designed to handle quick responses because they have really high clock speeds and really low latencies. However, this only holds true if the memory doesn't get saturated, and their memory speed can become a bottleneck. Also, if you need to pass a lot of data through them, their bad parallelization will quickly become a bottleneck. For the ones taking pictures, I have a QR code at the end of the presentation where you can get all the slides. It's on my LinkedIn profile. I will let it at the questions. Yeah. Okay. GPUs, on the other hand, they have a considerably high initial latency. So it's really bad for small amounts of data, especially when compared to CPUs. However, despite their lower clock speed and their high initial latency, because of their big bandwidth and their parallel execution, when sending more data through them, they can more than often make up and hide these latencies and come out on top in the end. Okay. When considering the throughput for machine learning models, CPUs aren't designed to be that great. They simply don't scale for large amounts of data, and they surely don't scale for large amounts of models. So generally, CPUs may not provide sufficient throughput for largest volumes of data. GPUs, on the other hand, are well suited for this. They are designed for parallel execution on large amounts of data, and they usually provide excellent throughput. However, we still need to consider the cost of all these things. GPUs might be better in general, CPUs might be quicker, but everything comes through a cost perspective. I think it's safe to say that CPUs are generally less expensive. They are less expensive upfront, they are less expensive in operational cost because they consume way less power, so they need way less power to cool them. And also they are very accessible. You can always find the CPU somewhere. That is not true for GPUs. The last important thing is that they are really easy to work with. So this cost should also be taken into So another cost that should be taken into account for this is the opportunity cost and the development cost of working with CPUs rather than GPUs. GPUs, on the other hand, are more expensive around the board. They are more expensive upfront to buy, they are more expensive to run and to cool. Sometimes they are really scarce, which can jump in their prices, and they are harder to work with. So you need better technical expertise to work with them, more development time, which adds to more cost. Now, I've prepared some benchmarks for you, so we can look at some numbers and some concrete use cases for all of the metrics we detailed earlier. We look at how latency, throughput, and cost come together, and how this plays out in both the case of small models and for large models. Starting with small models. Here I've prepared a small BERT-like model. It's a transformer model, it's pretty small in size. In case you don't see, blue is for CPU latency, while red is for GPU latency. And I've prepared the cases for more sequence lengths. How big is the input data? And you can right away see, especially here at the low numbers, the initial latency of the GPU. It's high, no matter how small the packages is. That's not true for the CPU. However, as we go forward, they start to level off, and they start to have similar latencies for medium-sized data. Well, you might say that CPUs and GPUs are pretty similar. But once we start taking cost into considerations, things really start to flip. Here, CPU is the cost of CPU in green and the cost for GPU in purple. You can see a huge difference, especially for lower ones. You pay a lot for GPUs. They might be better or similar in performance on larger sizes, but because they are that much more expensive for small models, when you care about latency, there's simply no way you can feasibly use GPUs for it. What do you think happens at larger models? In case you don't see the red, that's because the CPU is in red. This is the latency of the CPU in blue, and in red is the latency of the GPU. You can barely see it. It was so bad that I had to make a logarithmic version of this graph, and even here, the differences are hard to see. For big models, the model I tested is a T5-like generative model, so it's an encoder-decoder transformer model. The latency on the CPU is so bad that there's no way GPUs don't take this one. In fact, I prepared a use case that you can also sympathize with. If you use ChatGPT, the average response time for GPT-4 is around 20 seconds for a full response. Now, I made a quick estimate based on some extrapolated data I tested from the Llama model. I tested it both on CPU and on GPU to see how the latency scales. And from my estimations, which surely need to be taken with a grain of salt, but the intuition is there, an average response time, if ChatGPT would have been deployed for CPUs, I estimated it at more than half an hour. Imagine staying half an hour for a single response for ChatGPT. I think it's safe to say OpenAI wouldn't have scaled so well in that case if their deployment would have been efficient. Now for the latency, the CPU is in green, the GPU is in purple. Sure, GPUs are that much more expensive, but because they are so fast, if you really care about latency for large language models or large models in general, GPUs are simply your only option. We can see this in Tesla, we can see this in OpenAI. GPUs are their only option for user-facing applications. Okay, now for throughput. I've simplified things a bit. The CPU is in blue, the GPU is in green, and it simply measures the amount of predictions one can do per second. And it's pretty close. The GPU surely wins. It is designed for throughput, but it's a close fight. The CPU isn't completely demolished for the smaller models. And when looking at the cost, things flip. This is the amount of predictions you do for your $1. Even if CPUs are slower, because they are that much less expensive, CPUs win here. Still, not by a long shot. This metric will be highly influenced on your specific use case. So if your model is a bit bigger, if your GPU costs are a bit bigger, depends on your deployment, whether it's on cloud, whether it's on premise. This is the really interesting case where the balance can flip in the favor of another depending on their specific use cases. Now for the larger models, GPUs in red, they definitely take throughput home. They are that much better for large models, for big data. They are designed for this. CPUs have no chance. Even when looking at the cost, GPUs are that much more expensive, but still, it is your only cost-effective options to use them. And I made an interesting thought experiment for our use case. If you remember, I told you at the beginning that we analyze around 270 billion sentences a month. We at Veridion do have a vast repertoire of machine learning models, both big and small. So I tried to make an estimate if for the large models, instead of using efficient GPU deployment, we would have used CPU deployment. And my estimate was that from 270 billion sentences a month, we would have barely been able to process 26 at the same infrastructure. That is less than 10%. Just imagine the amount of compute we would have needed to compensate with if we didn't choose the right deployment option. Now, there is a difference for us in real-world coverage. We monthly support around 80 million companies that we analyze through many possible lenses. And I wanted to make another thought experiment and estimate, instead of having the optimized deployment for each of our machine learning models, the best case for the small models, the best case for the medium and large models, and we would have gone with a naive deployment of trying to balance things out, have only one deployment, the easiest one for everything. And from 81 million companies a month, while keeping the cost and infrastructure the same to keep things fair, we would have barely been able to analyze 5 million. That is the difference of worldwide coverage to only covering a country like Germany. Yeah. Finally, to make things simple, I made this decision chart to help you get into the right ballpark when making a decision about how to deploy your machine learning model. First, you need to decide what you want to optimize for. Latency, cost, throughput, maybe all of them. If you want to optimize all of them, you're on your own, because that is a hard path. Yeah, if you want to optimize for cost, then your only options are CPUs. They are the most accessible one, they are easy to work with. If you only care about cost, your only options is CPU. However, if you care about latency, then this depends. Is your model small? If your model is small, then CPUs are the better options, because they are low latency, they are fast, they are cheap. So from a real-world perspective, where you take both performance and cost into consideration, the best cost per unit of latency for small models are definitely CPUs. For medium and large models, though, you saw there is no chance. If you have any kind of user-facing application where your model needs to feel snappier, it needs to give inference requests fast, then GPUs are your only option. Remember the ChatGPT response in half an hour? Only on GPU can you keep it under 20 seconds. For throughput, though, this is our use case, and we are really familiar with it. All we care about is throughput. I added an extra interesting decision. Even if you care about throughput, are you sure you are really working with big data, millions or billions of rows? Because if not, I would recommend you still go on the CPU route. It might be less efficient, but it's much easier to work with, it's much easier to sustain, and depending on your operational and development cost, it might win in the end. It's definitely the easier route to go with. However, if you do have big data, then you really need to think about your deployment options. If your models are small or even medium, you saw that the CPU doesn't get oversaturated, and by simply having more CPUs and them being more cost-effective, so less expensive, they can definitely win in some cases. We took a big win by optimizing for CPUs at the beginning with our small and medium models instead of throwing them on the expensive GPUs. However, if you care about throughput, you have big data, and your models are large, then your only option will still be the GPU. They are designed for this. They are designed for high bandwidth. They are designed to efficiently execute a lot of parallel data, so that, in the end, will be your only option. Okay, in order to achieve all this, I naturally had the privilege of working with some amazing people in my machine learning team. They are some of the brightest and most hardworking people I've met, and they've helped build Veridion to what it is today. All of them passed a challenge in order to get here, a challenge that I have seen failed countless times. So if you care for giving it a shot, try scanning that generated QR code there and tell us what you think. Okay, now for the rest of the presentation, I've reserved the time for questions. Here, another generated QR code. Just get the slides. They will send you to my LinkedIn profile, and you can get the presentation there. Thank you.
Thank you. Thank you so much, Claudiu. I have a favor to ask you on behalf of the people here. Maybe you could switch a bit to the previous slide, because I saw some people trying to capture the previous QR. I think they're interested in your challenge. So
all of the QR and the slides will be available on the presentation as well.
Okay. I think we're ready for some questions. Thank you for a very well-structured presentation. I actually understood more of it than I thought I would. I am not very technical in the sense of AI and machine learning, but the way you explain things certainly made it easier to understand. And now let's see if someone from the audience, here we go.
Hello.
Hey.
Very good presentation.
Thank you.
First of all, I got two questions. So how do you choose, how do you control, after you deploy, you have a machine learning model, you want to deploy it, you want to run. How do you choose if it's going to be run on a CPU or on a GPU?
Well, I start off with the ballpark hunch feeling that I get. Is the model big? Is the model small? Does it have a chance to saturate the CPUs? What CPUs are available? And since we build our own bare metal clusters, we were very careful in choosing our hardware, both CPUs and GPUs. And in time, we simply had the experience. We tried the CPU route, saw how it works. We tried the GPU route for a month, saw how that worked, what are the problems for both cases. But in general, the simple rule of thumb law, is it big? Go for GPU. Is it small? Try the CPU. If not, simply test both and see which is better at the end.
No, but I meant on the technical level. So how do you choose? Do you have a tool which selects where the machine learning will run?
Oh, no way, no. So for each of our machine learning models, we have a custom deployment pipeline for it. It's an exaggeration to say that for each of one, but they are divided in some categories. So throughput optimized big models, throughput optimized generative models, which are a bit different, latency optimized encoder models. And for all of this, we have separate pipelines that we send on different clusters, on different devices. And we simply know at the development stage where that model will go.
And I was very surprised on the first slide. You said you made the cost reduction from 300K to 20K. That's incredible. So everybody's moving from premise to cloud. And if I understood correctly, you reduced cost by moving from cloud, from Amazon cloud to back to on-premise?
That is completely right, yes. By simply choosing our hardware specifically for our use case, so for our models, and being able to optimize this, that cost reduction, as I said, was calculated over a 2-year period. Even though the upfront costs were a bit significant, the operational costs are much lower. And the most important thing is that they allow us to optimize down to the cache level, to the core level, to the everything, in order to use the last hertz, the last memory clock on each of our devices. The cost for the servers, the cost for the electricity, the cost for running them, everything. When looking at a 2-year period, that is the cost reduction. It's 15x. Yeah.
Do we have other questions? Thank you for the question, by the way. Yep.
Hello.
Hey.
I have a question regarding the, what do you think about the future actually of the computing power? Because previously, if we will take the neighbor field, for example, mobile applications, in the start, everyone was aiming for the smaller parts, for the smaller applications. Now they are taking up to gigabytes.
Oh, I see.
Do you think that we will be going towards some devices which are like measuring from terabytes and so on, and it will not be possible to run such computations on, for example, lambdas and so on, which will be quite short, quite small, and will be executed really fast?
Well, I can certainly give you my take on this. When looking at the cost of building these colossal machine learning models, and as you have seen, they are sometimes in the hundreds of millions of dollars. Well, these are the costs on a country level, I don't know, nuclear reactor building or dam. So I can't see how this can scale up that much further. I think we are at or near the peak of how big these models will get, especially in the near future. So I think a period of optimizations where models actually get smaller and more efficient will come. So I don't think big changes in device infrastructure and memory sizes will be needed. Simply, we will use our existing tools better and not use large language models as databases and as search engines, and aim towards more of using them for what they're supposed to be, which are computational engines.
Thank you. We have time for one more question. Okay. I have a question, actually, building up to the previous one and your explanations for it. If we're going to see more smaller language models and seeing that more and more businesses are starting to deploy them, aren't we going to eventually see a scarcity regarding CPUs as well?
Well, I actually think it's going to be the opposite. Right now, everyone is jumping on the generative AI bandwagon, and everyone wants to have generative AI on their LinkedIn profile. So this is what leads to the scarcity in GPUs right now, because simply running one of these large models takes multiple GPUs. So if they get smaller and less expensive, you will have the option of running them on CPUs and smaller GPUs and not take half an hour for a prediction. So this will lead to simply a wild west of machine learning models everywhere, because they will be that much more accessible for everyone.
And another quick question regarding something Andrea said previously in her presentation, that not every business should start deploying AI and machine learning. Do you agree with that?
I definitely agree with that. If you can do it without machine learning, you should definitely do it without machine learning. And if you can do it with another tool and not use a 1 trillion parameter model instead of a MySQL database, then you should definitely go that way. It's better, more efficient, more environmentally friendly, whatever. It's better all around, and you can keep on that stigma and use machine learning when it's really needed.
Thank you so much.
Thank you,
Claudiu, Dima.